Section 5.5, using entropy to calculate the natural direction of a process in an isolated system. It's very simple. If entropy increases, that's the natural direction. If entropy decreases, that's impossible. What if the entropy remains unchanged? Well, then this system undergoes a reversible process, or the system has reached equilibrium. So let's look at one example. Let's say we have two objects. One at a higher temperature, T1 is higher than T2. We put them together, there's going to be heat flow. We know heat is going to flow from T1 to T2 because, again, T1 is higher than T2. Heat flows from this higher temperature object to this lower temperature object. We're going to prove that this heat flow causes the entropy increase inside this isolated system. All right? So when heat flows from object 1 to 2, we know this dQ2 is greater than 0 because heat flows into object 2, but dQ1 is negative. And then we can compute ds1 and ds2. ds1 is dQ1 over T1, ds2 is dQ2 over T2. We're assuming the heat flow is very slow to ensure it's a reversible process so that we can use this equation. We're assuming this is dQ reversible. This one is also dQ reversible. How do we compute ds total? It's very simple. It's just the sum of the entropy change of object 1 and object 2. We put them together, and we can combine these two terms because dQ1 is negative. dQ1 is negative dQ2. All right, over here. Heat flows from 1 to 2. dQ2 is the common factor. We take it out here. Now we have these two terms. We combine these two terms. The result is dQ2 times T1 minus T2 over T1 times T2. Remember, T1 is greater than T2. Therefore, this ds total is positive. The integral of this ds total, therefore, is positive. The entropy of the entire isolated system increases when heat flows from T1 to T2. When T1 is higher than T2, the entropy increases when heat flows from higher temperature to lower temperature. One more example, let's say an ideal gas expands against vacuum. Obviously, it's spontaneous and it cannot be reversed. But now let's compute the entropy change of the universe. So first, let's look at the system. If you look at the system, the volume changes under constant temperature condition. Therefore, the entropy change is nR times ln Vf over V initial. Why? It's an ideal gas, and it's expanding against vacuum. So there's no heat exchange, there's no work done, right? So what we can do is we can look at the final state. This is the final state. We have Vf final state over initial state times nR. What about the temperature? The temperature of the ideal gas remains constant. Again, over here, it's a constant. Why? Again, the interaction is between the system and the vacuum. Therefore, the energy of the system remains constant. Therefore, the kinetic energy of the system remains constant because it's an ideal gas. Therefore, the temperature is a constant. So anyway, delta S, that's the entropy change of the system is this. What about delta S surroundings? Well, the surroundings is vacuum. There's no change to it. So the sum of delta S and delta S surroundings is this guy. And this is greater than 0 because it's expansion. All right? So we can tell the expansion of an ideal gas against vacuum is a spontaneous process because this process increases the entropy of the universe. Now let's think about this process in the opposite direction. Can a gas, ideal gas, shrink, become smaller, and leave a space that's vacuum? Well, obviously it's absurd. And also we can know that this process involves the decrease of the entropy of the universe. Therefore, this process cannot happen.